this is a quick example of just understanding what R is and all that. This still isn't showing you how to compute it. We'll get to all that later. But this is just a data set showing this is the cost of pizza over several years. This is the cost of riding the subway in those same years. Alright, so this isn't different years, okay? The dot itself represents the year, okay? So in 1960, it looked like a slice of pizza was less than 50 cents, and the cost to ride the subway was also less than 50 cents. So that's where these 2 points are meeting. But anyway, the point of this is to show you that as the slice of pizza, as that price increased from $0 to $2.50, the cost of subway fare in this particular city is also increased from 0 up to $2.50. Alright, and that's what these dots are representing. Now, as time went on, the cost of pizza went up, and at the same time, the price of a subway ticket went up. So this data set shows a definite linear pattern in the scatter plot. The scatter plot is just these dots themselves. Alright, now this was the analysis ran on this data, and it showed that Pearson value, the R value, was equal to 0.988. Alright, so almost 1. 1 would mean that they're just in a perfect straight line. Alright, but because of this 2002, it kind of dipped out of line. It's not a perfect straight line, but it's still pretty close to a perfect straight line there. Alright, now what are we going to do with that 0.988? Obviously it has a linear pattern, so really that's all we would need there, but the way this method wants you to do it is we're going to base it, our interpretation of that R value, either on the p-value method, which that's the p-value here, right? We're not going to use that. We're going to use just the table from A5. So in your book, there's this table A5 in that fold-out flap, or if you use the electronic version, you can download the electronic version, and this is like the third or fourth page of it, something like that. Alright, anyway, that's what we're going to use to measure here. Alright, the way that this works is if your absolute value, just in case you have like a negative correlation, you always use the absolute value. If it exceeds this value from the table that we were talking about, these different values right here for 0.05 or 0.01 for your significance level, if it exceeds that, then you're going to say that there is a linear correlation between the two variables. Alright, so this particular data set that we have, there's 1, 2, 3, 4, 5, 6 data points. Alright, so according to the table, there's 6 at a 5% level of significance, or 0.05 level of significance. R would have to be above 0.811 for us to consider that there's a linear correlation. Alright, if we were doing a 0.01 level of significance, then it would have to be above 0.917. Alright, so that's what these are like. They're just like the critical values when we were doing hypothesis tests. They're like the cutoffs. Anything beyond this, and we'll conclude that it is linear related. Alright, so those are the cutoffs, and in this case, those are our positive and negatives depending on which kind of correlation we showed. Ours was positive. There's where our number fell, 0.9888. It's right here. There's our cutoff, 0.811. So we conclude that there is correlation. Alright. Had it been below that value, that 0.811, anything between there and negative 0.811, we would say there's no correlation, no linear correlation. And then again, if it had been negative correlation, meaning that as the price of pizza went up, the cost of a subway ticket went down, if it had been there, then we would conclude there's correlation. But ours was positive, so we're above 0. So anyway, there's your critical value, and again, that just came from the table. There were 6 data points, so 0.811 from this table A5, and there's where that number's coming from. Alright, anything bigger than that in absolute value, alright, meaning higher than that, between that and 1, or if you take the negative number below that all the way up to -1, then we would say that there is linear correlation there. Alright, here's another example. They're giving us, they want us to use the 0.05 level of significance, so again we're going to be in this column, the 0.05 column. And it says we have a R value of 0.117, alright, using a simple random sample of 62 pairs of weights and discarded paper. So we're going to use weight of the paper on one axis, the weight of glass on the other. Alright, now if you think about it, there shouldn't be any correlation here between these two, because the weight of paper is on one axis, the weight of glass on the other. The weight of the paper and the weight of the glass should be determined by how much of it there is, not by how much glass there is for the paper and how much paper there is for the glass. Alright, so they shouldn't have any correlation together, and that R value is kind of suggesting that, meaning that it's closer to 0 than it is to 1. But they want to know, is there enough evidence to support a claim of linear correlation between the two? Alright, the fact that the R value is that low to begin with would suggest no, but if we want, with this big of a sample, we increase the likelihood of variation in our sample. So we still want to check it out and make sure. So at 0.05, 62, if you look at the table, there isn't a 62, it just goes 45, 50, 60, and then 70. It's kind of out of the screen there, but 70 is the next number. So there isn't a 62, so we just go to the closest one. So our closest one here is 0.254. At this 0.05 level, where they intersect here is 0.254. Alright. And this R value is not bigger than 0.254. So that's what this is saying. The absolute value of that R value that we obtained up here does not exceed the 0.254. So we conclude that there's not enough evidence to support a claim of linear correlation between the weights of glass, weights of discarded paper and glass, period. Like for any sample we could come up with. The population is not linear correlated because our sample suggested that it didn't have linear correlation. So that's what we're doing here when we're interpreting R. Alright, R squared, if we square an R value, it basically is giving us a proportion of the variation that is explained between X and Y by some linear relationship. So at that previous example we did, we got an R value of 0.988 when we're talking about pizza prices and Subway fare. So that would mean that if we square it, we get 0.976, which would roughly interpret as around 97.6% of the variation in the cost of a Subway fare can be explained by the linear relationship between the cost of pizza and Subway fares. Alright, let me say that again to make sure you understand. We're saying that roughly 98%, 97.6% of how the cost of Subway fares changed over time can be explained by a linear relationship between pizza and Subway fares. Right? That's basically saying that only about 2% of the variation in cost of Subway fares can be explained by things other than pizza. Alright, that seems ridiculous, but that's what this R and this R squared value is saying. Alright, R squared is called the coefficient of determination, and it's given us a percentage of variation that can be explained by a linear relationship. Alright, obviously by that example, this is really important. Correlation does not imply causality. Alright, huge idea. Correlation has nothing to do with cause. So just because two things are extremely strongly correlated, again, this is almost one, meaning that there is an extremely strong correlation between Subway fares and the cost of pizza. Alright, well, obviously, when you're determining the cost of a subway fare, you don't run out and see how much pizza costs in that town. Um, they're not caused by one another. All right, both of them changed. This went up, cost of pizza went up, subway fares went up just because of the CPI, the Consumer Price Index, inflation. Just time went on and things became more and more expensive. So that was more of the cause, but the correlation still exists and still strong there between these two. So really important idea. Correlation does not imply causation.